Hello, this is a quick look at section 1.3 for our differential equations class. We're going to look at some modeling problems. We're going to go take a look at problem number 7 from section 1.3. Suppose a student carrying a flu virus returns to an isolated college campus of 1,000 students. Determine a differential equation for the number of people, x of t, who have contracted the flu if the rate at which the disease spreads is proportional to the number of interactions between the number of students who have the flu and the number of students who have not yet been exposed. Okay? So our solution will involve our x of t, the unknown function, the number of people with the flu at any particular time. The rate at which the disease spreads will be the derivative of x, and then the number of people who have not yet been exposed out of 1,000 people would be 1,000 minus x. So we have our information. Let's take a look at the problem again and translate the sentences or the phrases. The rate at which the disease spreads is going to be x of t. And then we want the proportionality constant, we'll just call that k. And then the number of interactions between students who have had the flu and who have not yet been exposed will be the product of the people who have had the flu, which is x of t, and the people who have not yet had the flu, so that's 1,000 minus x of t. So this is our differential equation. And then let's just write it out or rewrite it in Leibniz notation, and instead of x of t we'll just use x, and here we have x of dx dt is equal to k times x times 1,000 minus x. So that's it. That's problem number 7. Let's take a look at the next problem, number 9, and this is a mixing problem. Suppose that a large mixing tank initially holds 300 gallons of water and 50 pounds of salt has been dissolved. Now, pure water is pumped in at the rate of 3 gallons per minute, and when the solution is well stirred, it is then pumped out at the same rate. So our rate of water coming in would be 3 gallons per minute. Determine the differential equation for the amount of salt in the tank at time t bigger than 0. And then it's also asking us what a of 0 is equal to. So let's assign variables. A of t is going to be the amount of salt in the solution. We can measure that in pounds. And we're going to need some help with the rate of going in and going out. So let R be the rate of salt going in and out of the mixture. More specifically, we'll say R in for the amount of water going in and R out for the amount of water going out. So that's the rate of change of salt in the mixture. So R is the amount of salt coming in, and R in, and then R out is the amount of salt going out. R in has pure water coming in, so there's no amount of salt per gallon going in. So we can say there's 0 pounds of salt per gallon going in, and then we can multiply that by 3 gallons per minute, which is the amount of salt. And so really, the amount of salt going in is 0 pounds of salt per minute. Going out requires a little bit more work. The amount of salt in a tank is going to be A of t pounds, and then there initially would be 300 gallons of water in the tank. So the amount of salt would be A of T pounds per 300 gallons. And then it's getting pumped out at 3 gallons per minute. And so that reduces to A of T over 100 pounds per minute. That's how much salt is going out of the water. So remember that A prime of T is going to be R in minus R out. We have R in is equal to 0, and R out is A of T over 100. And so we have the differential equation A prime is equal to 0 minus A of T pounds per 100 minutes. So that just simplifies to negative A over 100. So our differential equation is dA dt equals negative A over 100. And then the other question is, what is A of 0? Well, since there's 50 pounds of salt, then A of 0 is going to be 50 pounds. So remember that A is in pounds, A prime is going to be in pounds per minute. All right, one more problem. This is problem number 18 from section 1.3. We have a cylindrical barrel S feet in diameter, and then it weighs W pounds. It's floating in the water as shown in the first figure. So this is our first figure, figure A. After an initial depression, the barrel exhibits an up and down bobbing motion along the vertical axis. And they want us to determine a differential equation for the vertical displacement y of t if the origin is taken to be in the vertical axis at the surface of the water when the barrel is at rest. So that's the origin. And then they want us to use Archimedes' principle of buoyancy or upward force of the water on the barrel is equal to the weight of the water displaced. And then we're going to assume downward direction is positive. We're going to assume that the weight density of water is 62.4 pounds per cubic foot, and that there is no resistance between the barrel and the water. All right. So before we begin, we're actually going to use Newton's second law. And the second law is force is equal to mass times acceleration. So we have force is equal to mass times acceleration. We're going to look at the weight of the cylindrical barrel as W, and we're going to try to find the mass out of that. So the weight is equal to mass times gravity, and then the gravity is, we'll just call it G, and then the gravity is going to be incorporated into the mass. So the mass is equal to weight times the gravity. And then we can rewrite our acceleration as y double prime of t. Y, remember, is the position of the cylinder with respect to the vertical axis. And so A of t is equal to y double prime. So we get our force is equal to mass, which is W over G, the weight divided by the gravity, times y double prime, the acceleration. Okay, so that's one way to look at the force. Now we're going to look at the force a slightly different way. We're going to take a look at Archimedes' principle of buoyancy. It says the upward force is equal to the weight of the water displaced. So let's take a look at the phrase upward force, and part of our given pieces of information was that we're going to consider the upward as, or going downward would be the positive y, and so upward would be negative. So the force going up will give us a negative F. And now the weight of the water displaced, we want to consider the weight. We have the weight density of water, and that's 62.4 pounds per cubic foot. And then we're going to multiply that times the volume of the displacement. Now the volume of the displacement is a little space that that the water goes up and down on. And so the displacement that we're looking at is actually a cylindrical, it's a smaller piece of the cylinder where it was pushed down, and that's how much water is being displaced. So it has a radius of s over 2, and then it has a height of y of t. And so the volume of that cylinder is going to be given by pi, the r, the radius, which is s over 2 squared, and then the height, which is y of t. That's the height of the cylinder. So according to the Archimedes principle, the buoyancy is equal to the force, and the force is equal to a negative, and then the weight density of the volume, or weight density of the water, and then the volume that the water has taken up. So that would be negative 62.4 times pi s over 2 squared times y, and that simplifies to negative 15.6 pi s squared times y of t. So now we have the force written in Newton's second law, and in the force written in Archimedes' law. And so we're going to set them equal to each other, and we're going to have a differential equation with y double prime and y involved. So we have w over g times y double prime from Newton's law, and then we have negative 15.6 pi s squared times y in Archimedes' principle. And so if we just solve for y double prime and simplify the y of t to just the y, we have y double prime, or d squared y over dt squared, is equal to negative 15.6 pi times the gravity times the diameter squared times y, the position, divided by the weight w. Okay, so that's our differential equation, and that's it for section 1.3.